All right, so is the screen visible for everyone as well? Okay, so today we are going to start a new topic, a new chapter of electricity and magnetism, right? E&M. Okay, so, all right. Okay, so before we do that, any questions from the previous last lecture about waves and oscillations? We ended with the discussion of resonance and damping. Oh, all right. Okay, great. So, okay, so we have talked about this thing. We have talked about gravitation, right? We have talked about the force of gravity. I'm pretty sure that in your AS course, you have also uh, gone through, discovered what are uniform, as in constant electric fields, as though they do not vary. And so in this topic, in A2 physics, we'll be developing those ideas further, and we're also going to introduce the concept or idea of the non-uniform fields, right? So you're more or less familiar with the idea of electric fields, right? Where you talk about these things that are positive charges and similarly negative charges and their effect on each other, right? So you're familiar with the fact that two positive charges or any two same type of charge are going to repel each other, and different charges are going to attract each other. So in nature, you just see that there are two types of matter, really, right? There are two types of matter. One type of matter is such that it sometimes that it always repels another type of matter. So for example, you have a matter over here, and then you have another matter over here. And if you see that so there are two types of, originally there was no such thing as positive or negative charges. Nature, it's just our way to specify or differentiate these two types of matter. There are just two types of matter. One is positive, or let's say that when these two are brought together, they tend to attract, they tend to combine with each other. Uh, and so if that's the case, then we said that one type of matter is positive, and the other type of matter is negatively charged. Now, this is the electrical charge on these matters, right? And if we bring the same type of matter together, then they repel, right? So you're already familiar with these ideas, right? Okay, so these were so far you are familiar with uniform electric fields, right? Electric fields. So you know what an electric field is, how it behaves, how charges, when they are put in this electric field, how are they going to behave, and how you're familiar with the fact that these charges, they have their own electric fields, right? But what's new? The idea of varying electric fields or non-uniform electric fields. Varying electric fields. So this thing that I'm calling varying electric field, this is also sometimes called changing electric field, changing with time, right? So the strength or the electric field just changes as time progresses. If that happens, it gives rise to a phenomena which we commonly refer to as magnetism. So changing electric field is magnetism, right? So what does that mean? That means that if I have any charge, suppose you have a positive charge, right? And you're already familiar with this idea that a positive charge will have electric field lines around it, right? I'm going to draw these electric field lines like this. These are radial electric field lines. They come directly outwards, right? Now, suppose that this positive electric charge is just sitting here doing nothing. What is going to happen? Nothing is going to happen. No interesting physics happens as long as it's an isolated positive charge. It just distributes a positive electric field around it. Now, we know that if I bring a negative charge here, then something interesting happens. Then because the field lines are going in this electric charge, negative electric charge, then these two charges are going to come together. That's something. That's when something interesting happens. But what if we do not bring any charge, but instead push or move this charge, right? So suppose give this charge a velocity. So the charge starts moving. Now, if the charge is moving, then there is changing electric field. At every point, obviously, the electric field will start changing. So now when it comes over here, there will be some electric field over here, right? But there will be no electric field on its previous location because the charge has moved from its position, right? So electric field changes as the charge moves. Now, when that happens, it gives rise to magnetism, right? It gives rise to something we call magnetism. Now, this is something very interesting, right? This is interesting because there is no such thing as, there is no such thing as magnetism on its own. Magnetism is just a consequence of electricity, right? Are you getting what I'm saying? Is everyone following along?
Yes, sir.
All right. Okay. So that means, you could go so far ahead to say that magnetism is really just an illusion that an electric field portrays, right? So we can go even more deeper. We can talk about relative motion, and then magnetism becomes even more absurd, right? Because according to someone, he might see the charge as stationary, but another observer might see the charge as moving. So these two observers would have a different perception of magnetism. One would say there is no magnetism as the charge is not moving. The other person would say that there is magnetism around this charge, so it has a magnetic field around it, and so it becomes relative to an observer. Okay, so you're familiar with the idea of gravitation, right? Gravity. We have talked about it. We devoted an entire chapter to gravity. And in gravity, we saw that the force of gravity is written as some constant times the source of gravity, right? The masses which produce gravity. And the force of gravity is in between these two masses. So I'll just call one m1 and m2 divided by the distance squared between these two masses. That was gravitation. Now consider another force, and it is exactly like gravitation, It varies predominantly inversely as the square of the distance, right? But it is, you can say, billion times stronger than the gravitational field, gravitational force. Now, I say that, right? But and some of you might be confused. How is it so strong? How is electromagnetism so strong? A very simple example is everyone has a fridge at their home, a refrigerator. Some people, we put magnets on our fridge, right? Some just decorations or anything. You know that you can put a decoration piece on a fridge, attach it with a magnet. The magnet, there is electromagnetic force that is keeping this magnet held to the fridge. And then there is another force acting on the magnet, which is gravity, which is the weight of the magnet. But the magnet does not fall. In fact, if you try to remove the magnet from the fridge, you have to, work against it, apply some strength to, just to get it off the fridge, right? Same is the case when you open the door of the fridge or the freezer. This demonstrates the strength of magnetic field. It is so strong compared to the entire Earth. The entire Earth has a gravitational field which is pulling on this magnet to bring it down to the surface of the Earth, back to the surface of the Earth, right? But only a small tiny magnet that is attached to this decoration piece, a small tiny, it's a very small, sometimes it's a circular, like a magnet this much size, is attached to this decoration piece, and then it is attached to the fridge. This tiny magnet is capable of being held to a fridge via the electromagnetic force, while the entire Earth, which is pulling on this magnet, is not able to bring the magnet down. Isn't that incredible, by the way? This really gives you a picture of how strong the magnetic field is when it's compared with another very familiar type of force, which is gravity. And I say very familiar because the expressions for these forces is familiar. So I'm going to write down an expression which is the topic of, in fact, Coulomb's law, or in fact, this expression is also known as the Coulomb's law, right? And the Coulomb's law states that the electromagnetic force, the electric force, in fact, the electric force that the charges would experience is equal to some constant times the two charges, Q1, Q2, and it also varies inversely as the square of the distance between the two charges. So in case of gravity, we had two masses, right? We had two masses like this. Suppose there is the sun, there is the earth, and this is mass 1, this is mass 2. The force of gravity between these two was given by this expression. Now we consider two charges. There is one charge plus, and suppose any other charge minus. I'm just going to call them for now Q1 and Q2. Now it's the expression, the nature of the formula is exactly the same as gravity. So there are these two charges, Q1. Now, instead of the force depending on the mass of these charges, it depends on another property that is called a charge of these charges, or this matter, right? But it still varies exactly as the inverse of the square of the distance between these two charges. And then there is also another constant associated to this equation, which is I'm calling it K. The value for K is 1 divided by 4 pi times epsilon. Epsilon is also it's a constant, right? It defines the permittivity of space, but a space that is free of any forces, right? It's just free space, vacuum, right? So it defines the permittivity of that free space. This constant is also, it plays a very important role in determining the speed of light, right? But anyways, this is the expression for force of an electric charge, the force between the two electric charges. You can see that it depends on the magnitude of the charges of these two bodies, Q1 and Q2. And it also, again, depends on the distance between these two bodies as the inverse square law. Right. So any question up until this point? All right. No. Okay. So, all right. So that's Coulomb's, this law of force. How can I write down the electric force between two charges is known as the Coulomb's law, right? Okay. So the important point for this Coulomb's law is that you have to understand when is it applicable. So there are some conditions where the law is applicable. As it turns out, it is not the complete description of the electric force, right? To understand electric force, just as though this expression for force was not the complete description of gravity. We have discussed this very slightly, that gravity is much more than this expression over here. Gravity is actually the geometry of something which is called space-time. And this is not the complete description for the electrical force. More or less, you can say that yes, this describes the electric force, but you will also have to consider magnetic force, because electricity and magnetism are the same thing. So I'm going to give you one or two conditions when this thing is going to be applicable. So conditions for the validity of Coulomb's law, right? First of all, Coulomb's law, you have to make sure that you are using point masses or point charges. So the law is only applicable to objects like points, right? Point charges. The charge should be uniformly distributed. Either it should be uniformly distributed or it should be a point charge. You know, even when we consider spherical bodies, we consider spherical bodies, and we say that the charge, we can assume that if there is a body like a sphere, then all of the charge is concentrated at the center of this spherical body. But you have to, you have to make sure that these two bodies, obviously there's this electric force between the two spherical bodies. The distance between these two bodies is very large. And that makes sense, right? Why does that make sense? That makes sense because imagine if I were to view a very massive star from a very distant place, For example, when we suppose that I'm sitting on Earth and I use a telescope or use my eyes to see a star very distant, further away. This star appears as a point to me. You know, when you see the night sky, you see dots in the sky, which are stars. But they're not really dots, they're not really points. When if you are to able to get close to them, they're very huge objects, very huge bodies. And so if I were to consider two spheres that are infinitely further apart from each other, then they can be considered as point charges. Is that clear? Okay, all right. So we can compare and see how strong the electric force is compared to the force of gravity. Now that we know that suppose this is force of gravity, right? Force of gravity is G m1 m2 divided by r squared, and the electrical force is K q1 q2 divided by r squared, right? Now suppose that I take a body and these are two bodies, and suppose they're same masses, same mass mm. The distance between the two bodies is some r, and I'm going to use some values, use some numbers here to make my calculations easier. I'm going to say that they're further apart 1 meter. Both the bodies weigh 1 kilograms, and now I'm going to also say that the charge on both the bodies is 1 coulomb, right? 1 coulomb and 1 coulomb. Now let's do something. Let's put these values in these expressions. So of course, if these bodies have a mass, then they'll experience gravity. And if these bodies also have a charge, then they must also experience electric force. Is that right? So if that's the case, then I can compute these two expressions, right? And then I can see how, compare them, right? How do I do that? I'll just put in these values. So let's put, we see that the force of gravity is equal to G times, these things are 1, right? So 1 times 1 divided by 1 squared. So all of this is just 1. So this is just G. And the force of electrical force is K times, again, charges are 1 divided by 1 squared. So this is just some K. Now, the value for G is 6 point something. It's 6.67 into 10 raised to power minus 11, right? And the value for K is approximately 8.99 into 10 raised to power 9. And just by comparing these two, it is crystal clear that the force of electricity is 10 raised to power 9, which is a very big number. While G, which is 6.67 into 10 raised to power minus 11, it is a very small number, 0.00000000. There are 11 zeros in front of that 0.0. And then you see 667. So it's a very small, minute number, especially when it's compared to this number, which is a very big number, 8.99, and then there are 9 zeros in front of this number. So it's a very big number. And if that's the case, then to see the relation between these two, I'm just going to take the ratio, just divide these two numbers. So you can divide this K divided by G. And when you do that, dividing these two numbers, you get something into 10 raised to power 20. What does that mean? That means that the electrical force is 10 raised to power 20 times stronger than the gravitational force, right? So this means that the force of electricity is equal to 10 raised to power 20. And if I bring that over there into the force of gravity. So that's just to give you the idea of how strong the force of electricity is when it's compared with gravity, right? So is that clear? Any questions from this thing? Okay, I'll assume clear. Okay, clear. All right, so now we can talk about electric field, right? And let me tell you why do we need to talk about electric field. Okay, so you might say, we know we have discussed electric force. Should that not be enough? We understand the physics behind what's happening between the charges. We can use the expression for force, and we can understand all the dynamics that is happening due to charges. Well, so that's true. That's very true. You having the Coulomb's law, you have more or less everything that you need to compute or understand the dynamics of the charges, but you have to talk about something which give rise to these charges and then to the force on the charges. So it really turns out that the space is actually filled with a fluid-like substance, and this fluid-like substance is spread over across the entire universe, right? And there are multiple of these. So for electric force, this fluid-like substance is the electric field. It's like you see a very big ocean of water, and then when you see you throw a stone in that ocean, you see some waves forming, or if any disturbances happen, there are some waves on that ocean. In exactly the same way, we have electric field. You can think of it as a sea, an ocean. In any disturbance in this electric field gives rise to the charges, positive or negative. And so the charges are a consequence of electric field itself, right? And so if I have this electric field, suppose this is my electric field, if I put another charge in this electric field, it's going to experience something. If I put another charge in this electric field, the charge experiences something, and that's the force. That's the electric force. So the electric force is also a result of the electric field. So you can, in very simple words, you can define an electric field as a region of space. It's a region of space normally around a charge. And if I bring any other charge in the vicinity of this space, then it will experience an electric force. So if I bring another charge in this field, it experiences a force. Right? And so that's how you can experience the attractive force between two unlike different charges. So here what happens is, if I have a positive charge, it creates an electric field around it, which we drew before as the radial lines going outwards. And now if I bring, so if a negative charge is sitting over here outside this field, right? Suppose it's sitting over here and its field is outside this thing. So it's like completely separated, isolated from each other. Nothing is going to happen. But as soon as this whole thing, it starts coming closer towards the positive charge, the negative charge starts coming. So you can see the screen, it's coming closer, closer. And as soon as it enters the vicinity of the field of the positive charge, then it will immediately experience this attractive force, and then it will attract towards the positive charge, right? So that's electric field. And for positive charge, it's a convention. We take it by convention that for positive charge, the field is directly outwards from the positive charge, while from the negative charge, it's directly inwards to the negative charge, right? So is that clear? Is there any question from this? Okay, so let me see, how much time do we have left? 3 minutes. All right, so that's electric field. Now we can also talk about the strength of this electric field. How strong will the electric field be? What would affect this electric field? As in, what factors does this electric field depends on? So you can define a variable called the electric field strength. And this simply measures how strong will the electric field be. So if I have this electric field and I put a charge in it, how strongly will this charge experience the force on it because of this electric field? That's what the electric field strength measures. So you can define or describe it as the force, specifically the electric force that a charge may experience at any point in the electric field. Now, you may keep a reference charge in your mind. Usually we define it as electric force per unit positive charge. So doing so, this helps us keep the track of our signs later on. So we say that electric field strength is the electrical force experienced per unit positive charge at a point in the electric field, right? So that's the strength of the electrical field. Now, suppose that if I have, I'm going to draw a charge and I'm going to give you a visual picture of this electric field strength. How does it change, right? So suppose I'm just drawing some axes. Don't mind the axes right now. So here we have the distance between the charge. Here we have the electric field strength. All right, so suppose that if I have a spherical charge placed over here, right? And suppose that this charge is a positive charge. There will be field lines coming outwards from this charge, right? We have discussed that. And so I can show how does the electric field varies as I move around this charge. So when I'm inside the charge, you will not experience any electric field. There will be no electric field experienced inside this charge. So suppose we are inside this charge up until these points, right? So I'll use another color. So there is no electric field experienced. As soon as you start moving outside, so on the surface of the charge, the electric field is maximum. On the surface of the charge,